talk about the periodic table of elements. So an element is a substance made of one type of atom. So it cannot be broken down into any other substance. It is entirely that one atom. Oxygen cannot be broken into anything other than oxygen, right? So this is kind of like having a prime number in math, right? Now, Dmitri Mendeleev, he's our guy here. So Dmitri Mendeleev is the first one to really notice that some elements seem to have similar properties. And once he notices that, he decides he's going to figure out a way to organize them. So in 1869, he's actually going to make the first periodic table. Now, when this happened, we only had 63 elements. So there were giant gaps in his periodic table. But he says, we're going to be able to figure out what kind of properties we're going to see in these elements based on where they would lie on the periodic table. So basically, where you are on the periodic table helps to determine your properties. So he's going to make this prediction that we're going to find an element that reacts this way when exposed to water, or that has the same set of properties as these but has a heavier mass. So it turns out Dmitri Mendeleev is correct. So we have 118 elements in today's modern periodic table, and they lie exactly the same way that he predicted they would, right? Where we find gaps, we also find elements. So our modern periodic table is simply a chart. I know it looks intimidating, but it is very simply just a chart of all of our discovered and created elements, because we can make elements in labs now, which is pretty cool. So our elements are arranged by atomic number and atomic mass. So each element has a 1 or 2 letter symbol. So we've got C for carbon, W for tungsten, and SN for tin. TIN is SN. So these are based off of their Greek, Latin, or English names, which is why you get tungsten's a W and tin is SN. So each block for each element on the periodic table is going to look something like this. This number up here is its atomic number. So the atomic number is the number of protons present in an atom. Now, if this atom is neutral, if it has an overall neutral charge, it's also going to be the same as the number of electrons, because if I have 2 protons and 2 electrons, I've got +2 and a -2, which are going to cancel out and going to make that neutral. So as long as our atom is neutral, our atomic number is also going to be its number of electrons. Now, big letter in the center, simply its symbol. So this is going to be a way we stand in instead of having to write carbon over and over and over and over again. All right, and this bottom number here, so this is its atomic mass. So atomic mass is really interesting. So this is the mass of one atom of an element, is its atomic mass. So we talked about when we've got our parts of the atom, that big heavy nucleus, and the electron cloud is light and fluffy, right? So the electron cloud is so lightweight that we can essentially assume its weight is 0, which means the atomic mass, the mass of one atom of an element, is going to be however many atoms or however many neutrons you have, plus however many protons you have. Both neutrons and protons have a mass of 1 atomic mass unit, right? Which means if I have 6 protons and 6 neutrons, I'm going to have an atomic mass of 12, because 6 times 1 atomic mass unit gives us 6 atomic mass units for protons. 6 times 1 atomic mass unit gives us 6 atomic mass units for neutrons, and 6 plus 6 is 12. So very simply, your atomic mass is going to be your neutrons plus your protons, because the nucleus is where an atom has all of its weight. And then again, atomic number is going to tell us its number of electrons as long as that atom is neutral. All right, so we said the periodic table is just an organized chart. Here's how we organize it. So we're going to organize it first into periods and then into groups. So periods are the horizontal rows on the periodic table. So it runs across, just like a sentence ends with a period and you write sentences horizontally, your periods are going to be horizontal. So across a period, if you start here, you always start left to right, same way we read. So if you start left and you move right, atomic number, atomic mass, and means the number of valence electrons is going to increase as you go across. So our periods, we're going to see an increase in valence electrons, an increase in atomic mass, and an increase in atomic number from left to right. Now, transition metals, they're this section in the center, right? So our transition metals, this group right here, they're going to be a little irregular. So metals are a little funky when it comes to valence electrons, and so we've got to calculate them a little differently. So that means that they're really kind of an exception to this valence electrons always increasing. Atomic number will always increase across the center, atomic mass will always increase across the center, but valence electrons tend to be a little tricky there. All right, so after we've got our periods, we've got our groups. So groups are the vertical columns. These go up and down, right? So these are often known as families pretty regularly. So just like families each have their own last name, we've got our family tree that runs up and down through generations, our groups are going to run up and down. And just like families have names, our groups are going to have names. Our first group is our alkali metals, our second group is our alkali earth metals, our second to last group is our halogens, our last group is our noble gases. Those are kind of the big four, but they're each going to have names, right? So just like how you are typically pretty similar to the people in your family in some aspect or another, same group means it's going to have the same number of valence electrons. Since valence electrons determine chemical properties, if it's in the same group and it's got the same number of valence electrons, it's got very, very similar chemical properties. For instance, all of our alkali metals, every element in that first group is going to react really explosively with water. So, same group, same number of valence electrons, again, except for our transition metals, that's where we get a little tricky because of those valence electron numbers.